Hello, my name is Ava, and I'm going to be talking about some really powerful concepts that are pretty important for both computational and Olympiad geometry. Incircles. Before we define what exactly an incircle is, let's prove some theorems. Theorem 1, the tangent radius theorem. Let's define a tangent as a line that meets a circle at not 2, not 0, but only 1 point. Then, this line makes a right angle with the radius to the 1 point of tangency. From now on, we will use this theorem without proof. Using this theorem, let's prove a corollary that the only radius that intersects the tangent at a right angle is the radius drawn to the point of tangency. That way, we know that if some random radius intersects this tangent at a right angle, it must be the radius to the point of tangency. And this will be really useful later on. So the way we prove this is by our previous theorem, we know that the radius to the point of tangency is a right angle over here. And we look at what happens as we move towards this point, which the tangent originates from. So as we move towards this point, notice that this angle right over here, where this is the radius extended to meet the tangent, actually gets larger. And notice that this angle, this way, gets smaller. And so there's no way that it can ever be 90 again. So now that we've proved that, we move on to theorem 2, the two tangents theorem. So we have a point and a circle, and we want to prove that the lengths of these tangents over here are equal. So let's separate these two triangles in over here, and using theorem 1, first of all, we know that these are right angles, so let's just mark these on the diagram, and we also know that these are radii, which must be equal in a circle. Now, what about these two hypotenuses? Well, they're part of the same segment, so they are equal. And thus we have HL congruence, which tells us that these parts of congruent triangles must be congruent. And we are done. Now we finally get to the definition of an incircle. The incircle is a circle tangent to all sides of a certain polygon. It always exists for any triangle, but it may not exist for polygons with more sides. Its center is called the incenter, which is also the intersection of the angle bisectors. Now in theorem 3, we're going to be looking at the lengths formed by the incircle in a triangle. So let's say we have triangle ABC, and we want to find the values x, y, and z in terms of the sides, lowercase a, b, and c. So what I've labeled x here as, here's the in-touch point, and x is basically just the distance from B to the in-touch point over here. Now, how can we apply theorem 2? Well, we know that since these are both tangents over here, this is also going to be x, and this is going to be y, and this is going to be z. Now we have a pretty clear system of equations. We just have x plus y equals a, y plus c equals b, and x plus c equals c. How to solve? Well, we can just add all three equations together, and we will get 2 times x plus y plus c, since each variable shows up twice in the sum, equals a plus b plus c. Now we can divide by 2, and simply just subtract each of the first 3 equations from our latest equation, and we get the following. So now that we've proved theorem 3, let's go on to the final boss, problem G4 from the MMT Risky Writing Stallion round. So essentially we have triangle ABC with AB equals 11, BC equals 12, and CA equals 13. We let D be some point on side BC, and let I1 and I2 be the incenters of the triangles ADB and ADC. So incenter is the center of the incircle. We also know that the segment I1, I2 is going to be perpendicular to AD, and we want to find the length of BD. So first of all, we're defining the point X right over here as the intersection point of this segment with AD, and we notice that the two incircles appear to be tangent to the triangle at the same point, X. Now, why is this? Well, we can simplify the statement by rephrasing it a little bit. We can prove that I1x is the radius to the tangency point, and I2x is also the radius to the tangency point on AD with each of the two circles. So clearly, by the definition of an incircle, AD is going to be tangent to both the circles. And we also know that this angle right here is actually a right angle. So by the corollary that we proved in Theorem 1, we know that this is just going to be true. These are going to be radii to the tangent points. Now we know that this key observation is indeed true, and we can proceed from here. So what we've just proved in Theorem 3 is that this length over here is going to be equal to AD plus BD minus AB. And so let's write that out. So dx equals AD plus BD minus AB, over 2. And we actually want to express this in another way. So dx is also a tangent segment to the incircle of ADB. So we just looked at triangle ADB, now let's look at triangle ADC. So dx also equals AD plus DC minus AC over 2. Now let's set these two equations equal to each other and solve for x. So rewriting this first equation with the info we have in the problem and letting BD equals lowercase x, we have AD plus x minus 11 over 2, and rewriting this second one over here, we just have equals AD plus 12 minus x, and then minus 13 all over 2. Now, from here, we are going to set them equal to each other. Right now, we're just canceling out these 2's, so we have x minus 11 equals 12 minus x minus 13. Then we have 2x equals 12 minus 13 plus 11. X equals 5, and that is our answer. I hope everyone enjoyed, and thank you so much for watching.